Hi, this is Alex from devstories.eu. Mastering DeepChem, Episode 3 of 15. You read a paper claiming a new graph neural network achieves state-of-the-art results on chemical properties, but when you look closely, they used a custom data split, a proprietary dataset, and an obscure metric, making their claim mathematically meaningless. Standardized comparison is the only way scientific progress happens, and in computational chemistry, that standard is the MoleculeNet benchmark suite. A common mistake is thinking MoleculeNet is just a static repository. It is not a downloadable folder of CSV files sitting on a server that you have to parse and clean yourself. It is a curated, deeply integrated suite of datasets baked directly into DeepChem through the dc.molenet module. It serves as the ImageNet of molecular machine learning. It provides a shared set of tasks, standardized splits, and evaluated baselines across different domains. The suite categorizes its data into specific scientific areas to test different modeling capabilities. You have quantum mechanics datasets like QM9, which contains geometric and energetic properties for small molecules. You have physical chemistry datasets for predicting solubility or hydration-free energy. And you have biophysics and physiology datasets, including toxicity benchmarks like Tox21, which measures how thousands of environmental chemicals interact with specific biological pathways. Let us look at a practical scenario. You just designed a new toxicity prediction model, and you need to mathematically prove it outperforms previous baselines. You do not need to hunt down the raw Tox21 data, handle the missing values, or write a custom parser. Instead, you call the load Tox21 function from the dc.molenet module. This is where it gets interesting. When you invoke a load function in MoleculeNet, it doesn't just return raw text. It processes the data dynamically using a featureizer you specify in the arguments, like circular fingerprints or graph structures. The function typically returns a tuple containing 3 core elements. First, it gives you a list of the task names. For Tox21, these are the 12 specific biological targets you're trying to predict. Second, it returns the dataset itself, which is already neatly partitioned into training, validation, and test subsets. Third, it provides the transformers used to normalize or scale the data during the loading phase. You take that pre-split Tox21 training set, feed it to your new model, and then evaluate the predictions against the test set. Because every other researcher uses this exact same API and featurization pipeline, your final receiver operating score can be directly and fairly compared against published baselines. MoleculeNet also standardizes how you evaluate generalization through splitting strategies. The API supports multiple ways to divide your data. While you can use a basic random split, chemistry often requires a scaffold split. A scaffold split separates molecules based on their core two-dimensional structures. This forces the test set to contain molecular frameworks the model never saw during training. It tests if your model actually learned underlying chemical rules, rather than just memorizing small variations. By default, the load functions apply the splitting method that makes the most scientific sense for that specific dataset. The hardest part of applied machine learning isn't writing the model architecture, it's proving the model actually generalizes to unseen data without data leakage. MoleculeNet gives you the strict, standardized playground required to make those proofs stick. That's all for this one. Thanks for listening, and keep building.